Good morning, good afternoon, or good evening to you all. My name is Rihanna Macario, and for this video lecture, I'll be teaching you all about the 6th and 7th lesson of Pre-Calculus or STM 101, and that includes series and sequences and unit circles. So to give you an overview of our first lecture, I'll be talking about the definitions, differences, and examples of sequences and series, and the various types of sequences and series. I'll be also giving the definition, formulas, some examples, and techniques in finding and expanding the sigma notation. So to start, a sequence is a function whose domain is a set of positive integers or the set 1 to 3 until n. It is a list of numbers arranged in order following a pattern or formula. So to illustrate sequences, so if a sub 1, a sub 2, a sub 3 until n denotes the terms of a sequence, then 1, 2, 3, 4 until n denotes the position of the term. So meaning, a sub 1 is actually the first term, a sub 2 is the second term, and so on. So, in short, sequences are basically just a list of numbers separated by commas. And also, a sequence can be defined based on the number of terms. So sequences can be either finite or infinite. So a finite sequence is a function whose domain is a set of positive integers where n is given or known. Basically, we know the last term of this sequence or set of integers. So an example of a finite sequence is 1, 2, 3, 4, 5. So we know that it starts at 1 and ends at 5. So next up, the infinite sequence is a function whose domain is all positive integers, and it continues on into infinity. And as an example, an infinite sequence would look something like this: 1, 2, 3, 4, 5 with the 3 dots, also known as ellipses. This basically signifies the unending nature or the progression of integers until infinity. So we will not know for sure until what term it will end on because it is infinite. So a series represents the sum of the terms of a sequence. It is the summation of the numbers in a sequence. So earlier, we talked about sequences being divided by commas. So in series, you can clearly tell it's a series if it is divided or separated by additional sign or the plus sign. So in short, you're basically just adding up or summing up all the terms in the sequence. So like sequences, we also have finite and infinite series. So here, a finite series or the nth partial sum is the sum of the first n terms of a sequence. So the sum of the terms is denoted by S sub n is equals to a sub 1 or the first term plus the second term plus the third term plus so on until the last term, which is denoted by a sub n. So in this series, it is clear that we have the last term of this sequence. So in the infinite series, it is just the sum of all the terms of the infinite sequence. Now, we'll move on into the difference between series and the sequence. So a sequence is basically a set or a list of elements or terms or integers that follow a pattern, just that. Whereas the series is the summation of the elements, terms, or numbers inside a particular function or a sequence. So in sequences, the order of elements is important because of its nature of being separated by commas. If you change up the order of the elements in sequences, then it will mess up your formula and you can't get the common difference or the common ratio for that particular sequence. Whereas in series, since it is just separated by plus signs, the order of elements is not so important. So you can interchange it, but then for formalities and for simplicity's sake, it's still better to, have order. To simply differentiate between finite and infinite sequences and series, basically, in infinite sequences or series, you can clearly see the ellipses or the 3 dots, so look out for that. Next up, we have the types of sequences. So there are 4 main types, which are arithmetic, geometric, harmonic, and Fibonacci. A sequence in which every term is created by adding or subtracting a definitive number called the common difference to the preceding number is called an arithmetic sequence. So as an example of an arithmetic sequence, we have 1, 2, 3, 4. Given the sequence 1, 2, 3, 4, we can subtract 2 minus 1, which will give us 1, or 3 minus 2, or 4 minus 3. It will be the same because it is the common difference. So the common difference in that particular example is 1. And the formula listed here is for us to find the nth term of an arithmetic sequence. And this will be discussed later on with some examples. So next up, we have a geometric sequence. It is a sequence in which every term is obtained by multiplying or dividing a definite number called the common ratio with the preceding number. So in arithmetic, we get the next term by adding or subtracting the common difference, whereas in geometric, it is obtained through multiplying or dividing. The formula listed below can also help us find the nth term in a geometric sequence. Next up, we have the harmonic sequence. It is a sequence in which the reciprocals of all the elements of the sequence form an arithmetic sequence. The best known harmonic sequence, and the one typically meant when the harmonic sequence is mentioned, is 1, 1/2, 1/3, 1/4, and so on, whose corresponding arithmetic sequence is simply the counting numbers 1, 2, 3, 4, and so on in their reciprocal form. So that is basically the same with 1 over a sub 1, 1 over a sub 2, and so on. And lastly, we have the Fibonacci sequence. It is a sequence formed by Fibonacci numbers in which each element is obtained by adding two preceding elements, and the sequence starts with 0 and 1. So here, to get the next term or element, you first add the two terms. So 0 plus 1, you get 1. 1 plus 1, you get 2. 2 plus 1, you get 3. And 3 plus 5 will give you 8, and so on and so forth. So for the types of series, we have two. We have the arithmetic and geometric. An arithmetic series is the sum of the first n terms in an arithmetic sequence and is denoted by the following formula, wherein S sub n, or the sum, is equals to n divided by 2 times a sub 1 plus a sub n, where n is equals to the number of terms, a sub 1 is the first term of that sequence, and a sub n is the last term of that sequence. Where in contrast, a geometric series is the sum of the terms in a geometric sequence. The sum S sub n of the finite geometric sequence, as shown in your screen, where the common ratio is not equals to 1, is given by the formula S sub n is equals to the first term times 1 minus the ratio raised to n all over 1 minus r. So again, this formula is used to get the sum of the terms in a geometric sequence. So I have here a sequence, and it is our job to discern whether it is an arithmetic or geometric sequence. So as seen from the PowerPoint presentation, we first need to find either the common difference if it's arithmetic or common ratio if it's a geometric sequence. So here, to test it out, 7 minus 4 is equals to 3. 10 minus 7 is equals to 3, so it holds up, which therefore means that this is an arithmetic sequence. And next, to find the nth term, we use this formula, which is a sub n equals to the first term plus n minus 1 times the common difference. So in our case, the first term here is 4, and now we'll add that to n minus 1 times 3, which is the common difference. So we will get 4 plus 3n minus 3, which will give us 3n plus 1. So for example, we'll be asked to find the 10th term. So what you'll do is just substitute 10 into n, and that will give you the value of the 10th term. And next, we also might be asked to find the sum of the first n terms. And for this example, the first n terms will be 5, so n equals to 5. We have this equation, S sub n is equals to n over 2 times the first term plus the last term. So since n is equals to 5, let's substitute 5 into n, so that will give us 5 over 2 times 4, which is the first term, plus the fifth term, which is, in our case, 16. So after simplifying that, we will have 50. So 50 is the sum of the first 5 terms of the given sequence. Next, determine the first 3 terms of the defined sequence and give its associated series or sum. So to do this, basically just find the value of the first, second, and third term, and then add it all up. So to find the first term, just substitute 1 into n, so that will be 2 minus 1, which will give us 1. And to find the second term, or a sub 2, just substitute 2 into n in the given sequence, so that will give us 2 minus 2 is 0. And for the third term, it will be 2 minus 3, and it will give us negative 1. And to add it all up, it will give us 0. So that is its associated series. Let's now move on to the sigma notation. The sigma symbol is used to indicate a sum. Mathematicians use the sigma notation to denote the sum of a sequence. So for this sigma notation, which can be read as the summation of t sub I from I is equals to m to n, t sub I refers to the expression for each term of the summation. Basically, it tells us how to get each term in the sequence. For the lower part of our sigma notation, we have I is equals to m, where I is the index and m is the lower bound or the start index, which is shown below the summation symbol. So it basically tells us that it starts at the value of m, wherein it ends or stops at the value of n, which is the end index shown above the summation symbol. It is also important to remember that the index I increases from m to n by steps of 1. So if m were to be 1 and n were to be 3, so when solving, it will be 1, 2, 3. It will never be 1, 1.5, 1.8, like that, okay? As it will always rise by steps of 1. So for our first problem, we have the summation of 2i plus 3 from I is equals to 2 to 4. So it starts at 2 and ends at 4. We need to substitute the starting value of I into the equation or the expression. So that will give us 2 times 2 plus 3, which is 7, okay? And since I mentioned that the steps rise by 1, the next value of I will be 3. So substitute 3 into I, which will give us 2 times 3, which is 6 plus 3, which is equals to 9. And lastly, since it tells us that it ends at 4, we will end this at 4. So 2 times 4 is 8 plus 3, which is 11. Add it all up and we'll have 27. For the next example, we have the summation of j squared minus j from j equals to 3 to 6. So it tells us that it starts at 3 and ends at 6. So what we need to do is to substitute the starting value of the starting index, which is 3, into the expression. So if j is equals to 3, then that will give us 3 squared minus 3, which is 6. And next, rise up by 1, which will give us 4. So now, j will be 4. So the next term here will be 4 squared minus 4, which will give us 12. Next, it will be 5. So 5 squared minus 5 is equals to 20. And the last term here is 6 squared minus 6, which will give us 30. 6 plus 12 plus 20 plus 30 will give us 68. So that is basically it. The next type of problem that we might encounter when solving sigma notations is when we are asked to write each expression into sigma notation. So the first step here is to consider if it is an arithmetic or geometric series. And to do that, you can subtract it or divide it. So starting with subtraction, or to test if it is arithmetic, we have 24 minus 31 is negative 7. And to double check, 17 minus 24 is also negative 7. So that confirms that this is an arithmetic series. So next, we will determine the general equation by using the formula to find the nth term. So the first term in this sequence is 31. Add that to n minus 1 and multiply that to negative 7. That will give us 31 minus 7n plus 7. And if simplified, it will be negative 7 plus 38. And next, we can now determine the sum of the series and write it in sigma notation. So the final answer here is the summation of negative 7n plus 38 from n is equals to 1 to 5. And for the next number, or in this example, the first term negative 1 can also be written as a fraction as negative 1 over 1. We also notice that the signs of the terms alternate, so it's negative and then positive, and then negative and then positive, with a minus sign for the odd numbered terms and a plus sign for the even numbered terms. So we can take care of the sign by using negative 1 raised to k, which is negative 1 when k is odd, and positive 1 when k is even, right? So we can therefore write the sum as negative 1 raised to 1 times 1 over 1 plus negative 1 raised to 2 times 1 over 2, and so on and so forth until 100. So we would write the sum in sigma notation as the summation of negative 1 raised to k times 1 over k from k is equals to 1 to 100. And so now we come to the part of the tips and tricks or techniques in solving sigma notation problems. So firstly, we have one about the summation of constant terms. So given this problem, if we write this out in full, we get 3 plus 3 plus 3 plus 3 plus 3. And so the trick with these kinds of questions is to multiply 3 by the ending index, which is 5, which will give us 15. So in general, if we are asked for a summation of a constant n times blank, then we can write this. So basically, and so as you can see, you can just multiply c, the value of the upper bound value, which is n. So it will be n times c, or nc. And for the second trick we have is for the summation of constant terms times k. So earlier we only had 3, and now it's become 3k. So if we write this out in full, we get 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. Because the starting value is 1 and it ends in 4. You can just multiply 3 times the sum of 1, 2, 3, and 4, which is 3 times 10, which is 30. And so the sigma notation or the summation can also look like this. So here we have the 3 at the right side, but now we can actually move it to the left side so that we arrive at this summation or sigma notation. So in essence, you multiply the value of c, or in this case 3, with the summation of the starting value until the ending value. So that would be 3 times 1 plus 2 plus 3 plus 4 for this particular problem. Next up, we have the summation of constant terms plus k. So now it is k plus 2. So if we write this out in full, or if we expand the summation, which is the summation of k plus 2 from k is equals to 1 to 4, we get 1 plus 2 plus 2 plus 2 plus 3 plus 2 plus 4 plus 2. What you can do here is to just add 1 plus 2 plus 3 plus 4 plus 4 times 2. So in greater detail, we can say that from this equation or summation notation wherein it is the summation of k plus c, move c to the left side and then multiply it by n. So in this case, it was 4 times c, which is 2 here. So it will become 4 times 2 plus 1 plus 2 plus 3 plus 4 because it starts in 1 and ends in 4. So there you go. We can now move on to the 7th lesson of pre-calculus, which is all about unit circles. Angles in unit circle. An angle is formed by rotating a ray about its endpoint. Properly defining an angle first requires that we define a ray. A ray consists of one point on a line and all points extending in one direction from that point. The first point is called the endpoint of the ray, and we can refer to a specific ray by stating its endpoint and any other point on it. So for this example, we have E as the endpoint and F as the other point. So this will be called ray EF. An angle is the union of two rays having a common endpoint. The common endpoint is called the vertex of the angle, whereas the two rays are the sides of the angle. The angle shown in your screen is formed by the ray ED and ray EF. Angles can be named using a point on each ray and the vertex, such as angle DEF or FED. Just make sure to put the letter of the vertex or the common endpoint in the center. In angles, Greek letters are often used as variables for the measure of the angle. So we have here the alpha, beta, gamma, theta, and phi symbols. And so we will now be drawing angles in the standard position. An angle is said to be in standard position if the vertex or the common endpoint of the angle is at 0, 0 or at the origin, wherein the initial side of the angle lies along the positive x-axis. If the angle measure is positive, then the angle has been created by a counterclockwise rotation from the initial to the terminal side. If the angle measure is negative, however, then the angle has been created by a clockwise rotation from the initial to the terminal side. In essence, we start with two rays lying on top of one another. We leave one fixed in place and rotate the other. The fixed ray is called the initial side, while the rotated ray is the terminal side. In order to identify the different sides, we indicate the rotation with a small arc and arrow. So for the angle on your left, we can see that the arrow is pointing to the left, meaning it is going in a counterclockwise rotation, which means this angle is positive. No matter where the terminal side ends up, it will always be positive, or the angle will always be positive if the arrow is in a counterclockwise rotation or manner. Whereas on the angle on the right, the arrow is rotating in a clockwise manner. So it is rotating to the right. Whereas if the angle is positive, it is rotating to the left as seen by the arrow. So for more examples, we have here three angles that are drawn in the standard position. The first angle has 40 degrees, and as seen by the arrows, since it is a positive angle, the arrow is rotating in a counterclockwise manner or rotating to the left. And for the second angle, it is also positive. For the third angle, we have a negative angle, which can be said because it is negative 320 degrees, but also because of the way the arrow is rotating. Also, notice that the terminal sides in examples 1 and 3 are in the same position, but they do not represent the same angle, because the amount and direction of the rotation in each is different. Such angles are said to be coterminal. Coterminal angles will be discussed shortly after. But for more examples, I have here another picture denoting the positive angle and the negative angle. As practice, in the following figure, identify the terminal side of an angle in standard position with the given measure. And so to start, we must remember that this here is the initial side, and we are looking for the terminal side. And for the first degree measure, we have 135 degrees, and that tells us that since it is positive, the arrow will go in a counterclockwise manner or rotation. And we know that this is already 90 degrees as seen from the box or symbol here. And to make up for the other measure, we can subtract 135 minus 90, which gives us 45. And since the half of 90 is 45, we can say that it stops here. So now we have completed the angle measure of 135 degrees as seen in the red line. So now to determine the terminal side, we have here the ray OC. Second degree measure, we have negative 135 degrees. And since it is negative, we can expect that the arrow will go in a clockwise motion, or it will point to the right. So starting with the initial side here, so like before, we know that this is already 90 degrees. And 135 minus 90 is 45, which is the half of 90, which tells us that it ends here. The terminal side of the angle with the degree measure negative 135 is the ray OD. For the third one, we have negative 90, so it's as easy as this. So from this, you can say that the terminal side of the angle with the degree measure negative 90 degrees is the ray OE. And lastly, we have the degree measure of positive 405 degrees. But then we know that the circle is 360 degrees. And since it is a positive angle, we know that it is counterclockwise. So it currently looks like this. But then, seeing as it is over 360 degrees, what we'll have to do now is to subtract 405 and 360, which will give us 45. So in actuality, it will look like this. Earlier, we stopped here because we made a full 360 degree rotation. But since it is 405, and 405 minus 360 is 45, we added an extra 45 degrees. And so the terminal side of the angle with the degree measure 405 is ray OB. And so we can now move on to the conversion of degree to radian measures and vice versa. The circumference of a circle is c equals 2 pi r. If we divide both sides of this equation by r, we create the ratio of the circumference to the radius, which is always 2 pi, regardless of the length of the radius. Since a unit circle has a circumference 2 pi, a central angle that measures 360 has a measure equivalent to 2 pi radians. Thus, we obtain the following conversion rules. To convert an angle in degree measure to radians, we need to multiply the given degree measure by pi over 180 degrees. And on the other side, to convert an angle in radian measure to degrees, multiply the given radian measure by 180 degrees over pi. And now here are some examples showing you how to convert degree measures into radians. So first we have 60 degrees. What we need to do is to multiply 60 degrees with pi over 180 degrees. So this can be simplified to 1 and this into 3. And also take note that the degree measures will be cancelled out. So what will be left with is the final answer, which is pi over 3 radians. For the second example, we have 135 degrees. Multiply that to pi over 180 degrees, simplify it, and cancel out the degree symbols, and we are left with 3 pi over 4 radians. And for the last example, we have negative 80. So here again, multiply it to pi over 180 degrees, cancelling out the degree symbol and simplifying the terms, which will give us 4 pi over 9 radians. For this slide, we have examples showing you how to convert radians into degree measures. Earlier, we multiplied the given by pi over 180 degrees so that we can cancel out the degree symbol. But for this type of problem where we need to convert radians to degree measures, we need to multiply it by 180 degrees over pi so that we can cancel out the pi symbols, leaving us with degree measures. So for the first example, 5 pi over 6 multiplied by 180 degrees over pi. So this will be cancelled out. And when simplified, it will give us 150 degrees. Shown on your screen right now are the following commonly encountered angles measured in degrees. And now we can list the corresponding radian values for the commonly encountered angles measured in degrees of a circle. Going back, we have these examples again, wherein the terminal sides in examples 1 or 3 are in the same position, but don't necessarily represent the same angle because it is coterminal. Coterminal angles are two angles in a standard position that have a common terminal side. Two angles are coterminal if and only if their degree measures differ by 360. And if the given is 40 degrees and we need to find the counterpart of that angle, or its coterminal angle, just subtract 40 and 360. So 40 minus 360, because 360 is a full rotation of a circle, will give us negative 320. This next example here asks us to find the angle coterminal with negative 380 degrees that has a measure between 0 and 360 degrees, basically the positive measure, and between negative 360 and 0 degrees, which is the negative measure. So take note, a negative angle moves in a clockwise direction, so to the right. So the angle negative 380 degrees lies in quadrant 4, or the lower left part of the coordinate system, or the xy plane. And And so you can see here that negative 380 is added with 360, resulting in negative 20. But since the positive value is asked from us, we can add 360 again so that it will become 340. And to get the negative value, leave it as it is, so it is negative 20. And for the next topic, we have arc length and area of a sector. In a circle, a central angle whose radian measure is theta subtends an arc that is the fraction theta over 2 pi of the circumference of the circle. Thus, in a circle of radius r, the length s of an arc that subtends the angle theta is the following. In a circle of radius r, the length s of an arc intercepted by a central angle with measure theta radians is given by s equals to radius times theta, or radius times the angle measure. So to make things simple and short, to find the arc length of a circle, we need to multiply the length of the radius by the measure of the theta, or the angle. So this red part over here represents the arc, and its arc length is equals to s. The radius is the distance from C to B, which is the same from the distance from C to A. And to visualize this in a fun way, we can think of a pizza. So the pizza has a crust. That crust lining is what is known or referred to as the arc length of the pizza, or the circle. For a more comprehensive guide to finding the arc length, we have here a circle with a radius of 10 meters that subtends a central angle of 30 degrees. Since a given angle is in degrees, we have the option to convert it into radian measures first. To convert an angle in degree measures to radians, multiply the given degree measure by pi over 180. The given angle measure here is 30, so multiply that by pi over 180, which can be simplified to pi over 6 radian. And so, to finally find the arc length, following this formula, S is equals to radian times theta, or the angle measure. R, which is 10 meters, will be multiplied to pi over 6, which is this one, which will give us 5 pi over 3 meters. So that is the overall arc length of the circle with the radius 10 meters, which subtends a central angle of 30 degrees. But take note, we also have the option to find the arc length even if the given angle is in degrees. And to do that, we can use this following formula, wherein the theta, or the angle measure, is divided by 360 and is multiplied by 2 pi r. Next up, we have the area of a sector. To get the area of a sector given the theta in radians, we can use the formula wherein the area is equals to 1/2 times theta times r squared. And to get the area of a sector given the theta in degrees, we can use this formula. As an example, here we are asked to find the area of a sector of a circle wherein the given angle, or theta, is 90 degrees, wherein it has a radius of 5 feet. So the given theta here is in degrees. So we can use this formula wherein the theta divided by 360 times pi r squared will give us the area of the sector. So that will be 90 over 360 times pi times 5 squared. So 90 over 360 here, as you can see from this circle, can actually be simplified to 1 over 4, right? So it will now be the area equals to 1 over 4 times 25 pi. You don't actually need to multiply pi, and so take note, you don't actually need to multiply the pi too. So the final answer will be 25 pi over 4 feet. And now we have finally come to the end of our tutorial video. So to recap, we discussed the 6th and 7th lesson of Pre-Calculus, or STM 111. So firstly, we talked about the definitions, the differences and examples of sequences and series, and the various types of sequences and series. So again, sequences are separated by commas, while series are separated by plus signs. And there are 4 types of sequences, namely the arithmetic, geometric, harmonic, and Fibonacci sequence. For the series, we have 2 kinds, and it's comprised of the arithmetic and geometric series. The sigma notation is basically just used to denote the sum or the summation of terms in the sequence. And for lesson 7, we have the unit circle. We discussed the definitions, formulas, and examples of unit circles and its linear and angular measures, the formulas and examples of converting degree measures to radian measures and vice versa. We also discussed the definition examples of coterminal angles. And lastly, we discussed how to determine the arc length and the area of a sector in a unit circle. And so, thank you for tuning in, and I hope you learned something. This is Rihanna Macario now signing out, and I wish you good luck on your exams.